Hey, good morning, guys. We will start with example for multi-class classification that we didn't finish last time. Um, so last time we talked about classification of a multi-class problem with binary classification. So we talked about approaches like one versus all and all versus all. And then we covered logistic regression that actually classifies um, multi-classes at once. So it doesn't use some binary classification problems. So this was our data set. Then I built three logistic regressions. And this is how I plot these lines just using coefficients from these three linear models. Then I calculated the probability for this point. So this is how the numbers were obtained on the in presentation last time. Then I did the all versus all, so all pairs of classes classification. And finally, we can use the built-in logistic regression when we assign a linear function to every class. But there are different parameters. So if you use parameter one versus rest, which is one versus all, then it will actually build, if you have n classes, n linear classifiers. And decision boundary will look like this. So remember that some orange triangles were classified incorrectly. The default behavior is multinomial, which we covered last time when we create for every class linear model their own weights, and then we tune joint probability. So this is the default behavior, and let's see how decision boundary looks in this case. So what do you think? Which method worked better, one versus all or joint logistic regression? Just logistic. So do you have any idea why the logistic regression that we did problem solving last time worked better than multiple binary classifiers? There is a simple explanation. So when we use one versus all, um, we built classification for one class and two other classes. Then for another class and two other classes. So we kind of look separately at our classes. In case of logistic regression, we maximize joint probability. And joint probability looks at all classes at the same time. So that's why it works better. So there is one more example for handwritten digit recognition. The NIST data set with 8 by 8 pixel digits. You can represent them with a long vector of size 64 and tune the logistic regression, but you know it has different solvers. So if you use just maybe by default it's gradient descent. Oh, actually it worked. Oh no, I didn't train, sorry. Yeah, you'll get a problem with convergence. There are different, if you look at the function description, different numerical optimizers. So in this case, Newton optimizer will work better. So you can see that it converges. And then the result of classification here, so we can see that data set is pretty balanced. So we can use accuracy as the metric, but also this table contains the metric macro that we covered last time. And you remember macro averaging is stable for unbalanced classes. So 96%. And we can then apply our classifier to one of the data points, to one of the digits. So the label prediction is 6. And if we plot the image, it looks like 6. And finally, if you look at the coefficients of this logistic regression, you will see that this is the array of size 10. And how many classes do we have in 3 digits? 10, from 0 to 9. So in other words, it creates 10 linear functions. And if you plot the size of every vector of weights, the size of the vector of weights will be the same as the number of features. So we have vector W 0 or plus 0, and the size of this vector is 64, and we have 10 vectors. So exactly what we did last time. Okay, so today we will talk about Bayesian classification, also probabilistic method. So let's see if I have slides. So let's get started with review of probability a little bit. So assume we have a coin and we flip a coin twice. So the outputs can be heads, 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 tails, tails, heads, and tails, tails. And then we assign probability to every output. What if the coin is unbiased, what will be the probability of every event? Yeah, you can tell without raising hands. So to get heads is 1/2. No, I mean of this event. One quarter, 1/4. Yes, yes. Because we have 4 events, they all equally possible. Okay. So 1/4. So for every event. Now How can we write this in terms of probability? We can write that we have event, for example, now about 1/2. For example, if we had heads on the first flip, then we don't care what was the result of the second flip. And what is the probability of this event? 1/2, yes. And to write this mathematically, we can write this that it's the probability of the union of two events, of the event heads and of the event heads tails. And the main axiom of the probability says that if we have independent events, then the probability of the union is the sum of probabilities. So it will be the probability of the first event plus the probability of the second, and we get 1/2. So now let's think about the probability. Now I will introduce, sorry, I was using, uppercase probability. Now let's introduce random variables and denote by x1 the result of the first flip. First. And by x2 the result of the second flip. And now we can talk about the probability. I will use lowercase p to make the difference between random events and random variables. Now, these are random events, and these are random variables because x can take some values. For example, x can take can result in heads. So let's think about the probability that our but better to use second, that our second flip resulted in heads when the first flip resulted, for example, in tails. What is the probability of this? So it's called conditional probability. Ah? 1/4. So you flip a coin and you know the result. Then you flip the coin second time. So it won't depend on the result from the previous flip. So it should be 1/2 actually. Yes. But now let's you wanted to.
I was wondering if you were asking a question.
Yeah. But I realized, but yeah, what?
So the probability of getting heads after tails should be 1/2. Because P equals their independence will be equals H, and H equals PH, X. Yeah.
So okay, so this is our intuition that that if we know the result of the first flip, then the result of the second flip will have probability 1/2. Now we will put this intuition into formula, and this formula is called the conditional probability formula. So in numerator we have joint probability that the result of the first flip, and I'm using comma, but if you think about events, it will be intersection. So this will be numerator and denominator. Oh, sorry, I'm using capital. Sorry, I should use lowercase. And in denominator will be the probability of the condition. And now we will rewrite this in terms of the events. Then I use capital probability. So the first event is, oh, wait a second. I made a misprint here. X1 is T, X2 is heads. So the first event is TH, because this is the probability that we get tails in the first flip and heads in the second flip. And in denominator, what is the probability of the tails to get tails on the first flip?
Yes, and yes, and two options.
Two options. Yeah, so you're right. So it will be either TT, either TH. I- or TH, sorry, TT or TH. But this comma is different from this comma. So this comma, we consider these events as a set. And it's the same as union. This comma, in this case, we consider as intersection, that we have two results of the same experiment. So maybe it looks a little bit confusing. And the denominator can be written as the probability of the event tails tails. So these events are called in probability elementary events. So then we can write a probability of any compound event using probabilities of the elementary event. So now I have this probability of the compound event, and this will be the sum of probabilities of independent events. Okay, and now let's put the numbers here. What is the value of for numerator? What is the probability of tails heads? What is the probability of our elementary events tails heads? 1/4. Yeah. What is the probability of tails tails? 1/4. Okay. So now we have the classical scheme, which is called the probability class, when every event has the same probability. So and I want to write 1/4, but with this fraction 1/4. And this is 1/4 plus 1/4. And the result, what is the result? And you calculate this fraction, 1/4 over 1/2. It will be 1/2. So it's the result will be 1/2 that we actually expected just by our intuition. Again, this formula is not something it's just an axiom. So in probability, this is just the definition of the conditional probability. And on this simple example, it coincides with our expectation from the output, but there's no any other meaning of this. It's just a definition of conditional probability. That it's the joint probability over the probability of the condition. And in most cases, it makes sense. Okay, so now let's go to our classification problem. In case of classification problem, we have a target y and features x, and we want to calculate the probability that our target, let's say, equals to 1 given features x. So we will now make use of this formula for classification task. So let's just use this definition. So it will be a joint probability of the class and features over the probability of the condition of the features. And usually people just avoid to write random variable x equals value x, and they just write p of x. But this is actually the meaning of this is the false. The problem in case of classification is that typically we don't know the joint distribution. We don't know any distribution of the data. We just have a data. We have our data. But sometimes you can figure out a distribution of data for specific class. So you can, for example, get a distribution of x given class 1. And I know, for example, as you remember, we have points, and you can find the mean for class 1 and mean for class 0 or -1. So let's apply again our conditional probability formula to represent the numerator, the joint probability, through the conditional probability. And the joint probability will be the product of this conditional times the condition. But in this case, I will use condition on the class instead of condition on the data. And this formula now is feasible for classification tasks. Because, as I mentioned, the distribution of the data for a specific class, sometimes we can estimate what is the distribution of the class. What can we calculate the probability of class 1 and class -1? You did this in your homework. Yes?
Probability of the y target being 1.
Yeah, the proportion. Proportion, yes. You just count how many points of class 1, how many points of class -1, and divide by the total number. So now this also is feasible to calculate. What about the denominator? Denominator is also feasible. You can use the formula of total probability and then write the denominator as the probability of x given, for example, class 1 times the probability of class 1 plus usually you will see in the textbooks lowercase when we assume the real values of the target plus probability of x for given the other class distribution times the probability of the other class. So, but in practice, we actually don't care about the denominator. Because so we can write the same formula for another class. Let's write just copy paste. So I'm talking about two classes, but you can, of course, do the same for multiple classes. And you can see the denominator actually for both formulas will be the same. And if we want to compare probabilities, we should compare only numerators. And then we assign a class by the highest probability. So we will assign the class by the highest value of numerator only. So in practice, we will calculate only argmax of the numerator, and this is called poor man base. So this is the actually called the base formula in probability. But if we look only at the numerators, then it's called poor base, because we don't calculate the probability, but we will find only the mode of our distribution. The mode is the highest value of the distribution. So, yeah. By the way, this is called base formula. When you write the denominator using the total probability. And we will use wait a second. Poor with E or poor huh? Wait, I think I misspelled this. How do I spell poor man? P-O. Oh, just R. Oh, thank you. Poor man base. Wait a second. By base. Oh my gosh. Okay. Poor man base classification is based on argmax of these two probabilities. So how to write this, like maybe like that. But because they have the same denominators, we can take argmax only of numerators. Okay. Now we have the notebook to solve for today, where we actually will apply this method for classification problem. And in your homework also you will use this Bayesian classification. And also you will use another simplification of this approach, which is called naive Bayes method. Okay, so we will now cover this in our notebook. Problems 12. Okay, so here is our data set from the first class. Oh, what have I? What? Wait a second. Okay. So let's estimate the probability of classes P of y and the probability of the points given classes P of x given y. Because this is all that we need for classification P of y given x. So let's see. Where do I calculate P probability of y? Okay. P of y I calculate later. First, I calculate P of x. P of x given given y. And we should assume some distribution of our points. So let's assume the normal distribution. For normal distribution, we need just two parameters, as you remember, mean and covariance matrix. So we will assume the distribution for x, for the point x, or actually we can use the verb x for class 1 is normal with parameters mu 1 and sigma 1. And for class 2 or negative 1, well, actually here I have class 0. Class 0 is normal distribution. I think maybe I made a mess with indices. I think I used indices 1 and 2, but their labels are 0 and 1, so they shifted backward. So on whiteboard, they will be 1 and 0. So we assume that our points have different means. And I think it makes sense to you, for you, the average of blue points is different from the average of the brown points. Let's calculate first the distribution of x given y. This is the formula for normal distribution. It has mean and covariance matrix. And this is the formula for covariance matrix with variances on the diagonal and covariances on the off diagonal. But there is built-in function in scikit-learn, and we will use it which will calculate and mean and covariance matrix from the data. So here is example how to calculate. Oh no, I actually use class 0. Okay. So to calculate mean, I take the data with label 0 and calculate the mean. So my data looks like that. Let's see. So x of 0, uh, wait a second, y of 0, sorry, y equals 0 is the array on true false. So if I apply x of y equals 0, it will actually choose only lines corresponding to y equals true. So that's why this line calculates mean for class 0. And then we calculate covariance matrix with NP covariance of these lines. But for some reason, in NumPy, it assumes that data are in columns. So that's why I use also transposition, because we use typically data in rows. So if you calculate without transposition, the shape of this matrix will be the number of points times the number of points. But our shape should be 2 by 2 because we have 2 dimensions. I can show you that if you don't use transpose, then the shape will be weird. So if you use transposition, the shape will be expected. The number of dimensions times the number of dimensions. Okay, your turn. Just do the same for class 1. Let's copy paste this code. And when you implement this, we can plot. Here I plot the distribution for class 0. And your task is to add the plot for class 1. Let's see the labels. Oh no, I plotted for class 1. Add in the plot. Actually, I added for class 1. So your task to add for another class 0. Because, oh no, wait a second. Actually, I added for class 0. It's a little bit confused. Oh no, okay. Blue points have class 0. Okay, then it was correct. Blue points were class 0. Yeah, so I plotted for class 0 the multivariate normal. So, and it looks like this. This is the projection. In 3D, it will look like this. Like highest probability will be at the mean, and then the probability will decrease. Okay. So just add one more line, or maybe two lines, to plot these two lines, to plot this distribution for the first class. And you will get the plot with distributions for x given class 1 and x given class 0. See? Okay. And then we can uncomment this line, and it will plot two distributions for two classes. And the next step is calculate the distribution of classes. There's P of y, which is the formula is here, but you can use NP unique, and NP unique will return the counts of unique values. Um, and to get the probability, you should just divide the counts by the total number of the points. And this is how you can calculate P of y. And now we have everything ready for classification. We have distribution of Px given y, we have P of y. And finally, we can calculate P of y given x. Again, we won't use denominator, only numerator joint distribution, which we will rewrite using the conditional distribution. Then we calculate the same for probability that our point belongs to class 0, and then we choose the maximum value and assign label. Okay. So yeah, here is the formula. Yeah, and here is actually the solution. Y pred equals, okay, you don't even need to calculate that. So we calculate the probability of x with mean and covariance for class 0 and multiply by the probability of class 0. And we do the same, we calculate the probability of x given class 1 and multiply by the probability of class 1 and take our max. So the predictions look as follows. Zero, so ones depending on which of these two probabilities was the greatest. Well, it's not actually probabilities, these are numerators, unnormalized probabilities. And if you calculate the accuracy is 84%. If you use, for example, just linear regression, linear logistic regression, we can compare actually. I don't use the split on trains test. Mhm. Well, logistic regression is actually better. So now let's look at the naive Bayes approach. So in naive Bayes approach, we assume that the coordinates are independent. So instead of learning the joint probability on x1 and x2, we will only calculate the probability for one coordinate x1 and probability for another coordinate x2 and take the product. So this is the assumption of independence of the components. Yeah.
So it assumes that px1 is equal to just px1 from y to y
Yes.
is equal to just p to the union of all px ones over every single y class. In that case.
Oh, could you repeat again? Could you repeat again?
So it will assume, so it assumes that every single event that is derived from another event is equal to just that event happening by itself.
No. In our previous approach, we calculated the covariance matrix using both coordinates x1 and x2. So to calculate the covariance matrix, we used the entire matrix X. In case of naive Bayes, we assume that probability of X, and X has two components, x1 and x2. Given class, but I will skip now just to make it more clear. So in the previous case, we calculated the covariance matrix for two-dimensional vectors. In naive Bayes, we assume that components are independent. You can think about features like your homework. In your homework, you will apply naive Bayes for spam filter, and your points will be words, and you can naive Bayes assumes that these words are independent. Of course, it's not true because we have word pairs and so on, but it's a simplification. So, and in this case, we also can write this under assumption that our features are independent as probability of feature 1 times probability of the feature 2. And this approach is called naive Bayes. Naive because we assume independence of features, which is not true in practice. But it will make our life easier because we will need to calculate the one-dimensional probability now. Instead of covariance matrix, we will calculate only one variance, one number. So this is the difference. So okay, so the first step is to calculate so instead of joint distribution, we will calculate the distribution only for the first coordinate and then for the second coordinate. So we'll calculate. I will just copy paste ypred and make changes. I will copy paste this and make the changes. So instead of this multivariate normal t, I will use multivariate normal of x, but I will take only um, the first coordinate. Oh, but I need also to recalculate mean. Aha. And for mean, I will use only the first component. And from covariance matrix, I will use, you remember on diagonal, the first term is the variance. So I will use only the um, the first component from my covariance matrix. And then I should multiply this by the same, but for the second component. So for the second component, I will take the second coordinate. And that's it. Now I will do the same. I will just copy paste this. To our second term with multiplication by probability of the second class. And now we can calculate accuracy score. Oh, wait a minute, so low. I think it should be actually greater. So so instead of joint, you can calculate. Yeah, so we should calculate the product instead of joint distribution. We calculate the product of one-dimensional distributions. Okay. Oh, I think I didn't change sigma. Okay, in the second multivariate normal, I should use sigma and mu for the first class. Okay, that's why we have low score. Okay, now it should. Okay, now it works. So as you can notice, the score now is better than for not naive Bayes, and even better than for logistic regression. Okay, do you have any questions? So let's think about why the simplification of the model resulted in better score. So in our first approach, we calculated the joint distribution, we calculated the covariance matrix. In our naive Bayes approach, we used only the diagonal terms from this matrix. So we didn't use all the information, but the result, the accuracy is better. Which is a little bit counterintuitive. Like in first case, we didn't assume independence of the features. In the second case, we assumed independence of the features and get better score. What do you think? What is the reason behind it? Of course, it's not always. If it would be always the case, then people wouldn't call this naive. Basically, they would just use this method. But in our case, it worked better. So, any ideas or? So let's go just ahead. Actually, I will. I can also I can plot this plot, but for naive Bayes. Let's see, just to compare. Um, okay, I don't know. I don't to plot it. So, as you remember, we made an assumption that our S given a class has a normal distribution. For naive Bayes, we made another assumption that our X given class has not the two-dimensional, but is the product of one-dimensional distributions. U, let's say 1 sigma 1 times normal of u for class 1 component 2 sigma 1. So here we had 4 numbers, and here we had 2 numbers, and here we have just 2 numbers and 2 numbers, so 4 numbers in total parameters. But why actually we choose this distribution? Why did we choose this distribution? The answer is that I chose this distribution because it's as simple as it's built in NumPy. But nobody actually said that our data were distributed according to normal distribution. So this is not a problem, how to choose this, how to estimate the distribution of the data. And it turns out that in our case, the assumption of naive Bayes worked better. maybe if we would assume another distribution, it would work much better. Does it make sense? So it's just because for this data, the joint distribution maybe is less good model, and you can think about this just by observation. The points don't group into a cloud. So the joint normal distribution is not a good model for these points. But if you look at the projection on each axis, on x1 and x2, then they actually, especially for on this x, they will definitely, blue points will cluster to one cluster and brown points will cluster to another cluster. So maybe this assumption of the independent components works better for these points. Does it make sense? Okay, now I think we're done with problem solving. Yeah, you can submit this by the end of the day. Now I want to go to the homework and solve partially one problem from homework to make your life easier. Um, well, I had some slides, but I don't want to spend much time on it. So the difference between generative models and classification models. So that's why the first one is called kind of poor man bias because we want just to classify points, but we don't want the joint distribution on y and x. So if you learn the joint distribution on y and x, then you can generate, for example, the task is to classify an image as dogs or cats. Then in generative model, you should generate an image. You should be able to generate an image with your model, but also you can use the Marshall distribution and then you will get probability of class. In case of classification model, you just predict a class. And you can guess which problem is easier. Of course, classification is easier. There are some examples how we can use Bayes formula for medical exams. Like if you have one test, the probability of the illness will be this, and if you make two tests, then you can get a lower or higher probability. So yeah, this is the homework. In the homework, you will have two problems. One, to implement naive Bayes classification for spam, another to classify the metal part. So this is a data set. They somehow calculated what they call six-fold rotation features. So it doesn't matter, just two-dimensional features for every class, and there are four classes. And then they fit the normal distribution for every class Let's see how um, the four Gaussians are different for every class. And also they introduced the cost function. So cost fun to make the problem a little bit harder. For example, we can increase the cost differently for different parts. For example, if our model misclassified the bolt, then the cost will be increased by 0.7. If it misclassified the ring, let's see, no, it's the same. Well, but it reduces differently. So if it's, for example, correctly classified, then both it uh, returns lower score than if it's incorrectly classified, correct classified early. So it means that it's more important to classify both correctly than early correctly. So uh, and without cost function, the classification decision boundary looks like that. With cost function, it will look a little bit different. And in your homework, you will actually get these plots. Or maybe now we will, if we have time. Um, so, yeah, the first problem is just to implement softmax. This is the second problem with metal parts. And there is the third problem for the spam filter. So, upload data. Data looks as follows. You have features and you have classes, and you will have four classes. This is just the beginning of table. So that's why the class is one. Then I separate into train and test. The crosses are test points. The first assignment used Pullman base formula, or also it's called maximum posterior, because this is kind of the probability of flight is a prior information, but when we have information about X, then it's called posterior. Maximum a posteriori, that's why it's called MAP estimate. And here you just repeat the same that we did in class. You just calculate mean for example, mean for class 1, mean for class 2, mean for class 3. Then you calculate covariance matrices for class 1. Class 2 and so on. There was suggestion. I don't want to type all this. Um, And oh my gosh. And then we should calculate posterior exactly as we did in our problem solving. So, oh, in fit, okay, it's def. We should use self also. Self. Then you should calculate also the probability of classes. You can calculate self of class 1, class 2, and so on. As you remember, you can use just count function. And finally, uh, you um, calculate the posterior and okay. So we don't use the hard classification. So I don't ask to return the class. I ask to return the probability of class. So it will return um, four numbers for every point. And then based on these four numbers, actually the classification will be processed in this plot. So, okay, maybe I have more time with another class because with our class we covered the code from previous lecture. So you can watch the recording from, if I may make the recording from another class. And wait a second, maybe I can just show my solutions so they will be in this recording as well. Um, I mean, it's straightforward assignment, but it's always good to see the solution. So, yes, so we calculate the probability for y, the covariance matrices and means, and then posterior. Oh, actually, here I predict the classes. I take argmax. Oh, okay. I called this posterior. It should be called prediction. It will. So it's just a prediction. The argmax of the probabilities, and then if you plot the decision boundary, it will look as in the textbook. For the problem with cost matrix, we multiply our predictions by this cost and sum up the probability for like to classify our metal part as class 1 by negative 0.2, the probability to classify our point as class 2 by 0.7, and sum up all these probabilities. It's called weighted sum. Then we do the same for the second part, for the third and for the fourth. So the only difference from the previous one that we calculate, let's say in probability we take maximum, in cost we want to minimize cost, so we will take mean here. And also to sum up the probabilities with these weights, we should multiply this matrix by the matrix of probabilities. And yeah, so this is the solution for the case with cost, and then it will classify a little bit different our metal parts. Okay, let's stop here for today. Yeah, and see you next week. Yes, sorry, I will stop recording.